In this video, we'll list some basic rules for differentiation. Each of these rules follows from the definition of the derivative that involves computing the limit of the difference quotient. Because this method of computation can be somewhat involved, we won't provide all of the relevant computations in this video. Instead, our focus will mainly be on illustrating what these basic rules are and how to use them. At the end of the video then, we'll justify one of the rules straight from the definition, but we'll leave the justification of the rest of the rules for the interested viewer. So let's get started with our first rule, the constant rule. Because the graph of a constant function has zero slope, such a function will always have zero derivative. In other words, if c is a real number, and if f is the function which is everywhere equal to c, then f prime is the function which is everywhere equal to 0. We often use the notation ddx to denote the differentiation operator, meaning that when we apply this gadget to a function, we get the derivative of that function. So, in this case, we might also write that ddx of c equals 0. In a similar way, we can easily compute the derivative of a linear function f of x equals mx plus b. Because the graph of such a function has constant slope, namely m, it must be the case that the derivative of such a function is equal to m. In other words, ddx of mx plus b equals m. Next, we have power functions, that is, functions of the form f of x equals x to the n. For example, when n equals 2, we get the quadratic function f of x equals x squared. If you recall, in a previous video we actually computed the derivative of this function at any point x, and we found it to be 2x. Notice that for this derivative, the coefficient of 2 is actually the exponent that we started with. And, in addition, the degree of the derivative is 1 less than the degree of the function we started with. All of this behavior actually occurs in the case of general n too. Specifically, the derivative of x to the n is n times x to the n minus 1. This derivative is called the power rule. To remember it, just remember that the power, which is n, becomes the new coefficient, and the resulting power of the derivative is just n minus 1, which is 1 less than the power that we started with. In particular, if we take the derivative of x to the fifth, we get 5 times x to the 5 minus 1, or 5x to the fourth. The derivative of x to the 100 is 100x to the 99th. The rule also works when the power is any real number. This allows us to find the derivative of the root function, for example. Indeed, because the square root of x is x to the 1/2, we can differentiate using the power rule to find that the derivative is 1/2 times x to the 1/2 minus 1 power. That is, 1/2 x to the minus 1/2. Many functions are sums of simpler functions, so it's useful to consider the derivative of the sum too. The rule for such a situation is simple. The derivative of the sum is just the sum of the derivatives. For example, if f is the function x to the third and g is the function 4x plus 5, then the derivative of f plus g is given by 3x squared plus 4, since 3x squared is the derivative of f and 4 is the derivative of g. All of these rules can be used in conjunction with one another too. For example, suppose we want to compute the derivative of this polynomial. Well, since the polynomial is a sum, its derivative will be a sum too of the respective derivatives, each of which can be found using power rule. For the highest degree term, we first pull out the factor of 3, and then we apply power rule to x to the third to get 3 times x squared. In total then, the derivative of this term is 9x squared. For the next term, we do a similar thing. We first pull out the factor of minus 5, and then we differentiate x, or x to the 1, to get 1 times x to the 0, which is just 1. So the full derivative of this term is just minus 5. The derivative of the last term is just 0 by the constant rule. Adding everything together, we find that the derivative of the full polynomial is 9x squared minus 5. This completes our list of basic rules of derivatives. To conclude then, let's discuss the justification of one of the rules, namely power rule. That is, let's show that the derivative of x to the n is n times x to the n minus 1. For simplicity, let's consider the case when n is a positive integer, such as 1, 2, 3, etc., because we claim that a proof for any of the other cases of n is actually similar to this one. For the derivative, we have to compute the limit of the difference quotient. It turns out that in this case, it's useful to use the alternative difference quotient from the last video, the one that looks like f of x minus f of a all over x minus a. Using our definition of f then, we find that the limit becomes x to the n minus a to the n all over x minus a. At this point, we're not able to just plug in a to compute the limit because both the numerator and the denominator go to 0. So we need some sort of clever method to compute this limit, such as an algebraic manipulation. In this case, there's a trick, and it's the following identity, which says that x to the n minus a to the n is equal to the product of x minus a with x to the n minus 1 plus ax to the n minus 2 plus a squared x to the n minus 3 plus plus a to the n minus 2x plus a to the n minus 1. In other words, the second factor on the right is the sum of all of the monomials that can be formed from the powers of x and a, where their total degree adds up to n minus 1. The reason this identity is true is just some simple algebra. In particular, we can expand the right-hand side by distributing the x term over the sum and then the minus a term over the sum. Multiplying each term by x raises the power of x by 1, whereas multiplying each term by minus a raises the power of a by 1, while also putting a minus sign out in front. By arranging these terms carefully, we see that actually a lot of them come in pairs, where one term in the pair has a plus sign out in front, but the other term has a minus sign. Adding them all together then, in the sum, we can cancel each of these pairs, and we'll just be left with whatever terms don't have a pair to cancel with. The only terms without pairs to cancel with are the terms x to the n and minus a to the n, which constitute the only two terms on the left-hand side too. Equipped with this identity then, we can use it in the numerator of our difference quotient, and, upon doing so, we see that there's a factor in the denominator which appears in the numerator, namely the factor of x minus a. So, after reducing by this factor, all we're left with is the limit of the big sum term. Now, the derivative requires us to take a limit as x goes to a. Such a limit for this big sum is easy, we just have to plug in x equals a. When we do so, because each monomial has total degree n minus 1, we see that every term will just be a to the n minus 1. And how many terms are there? Well, note that the powers of a actually count the terms, except this counting starts at 0, because the first term has a power of 0 in a. Since the last power of a that appears is n minus 1, this means that there are n minus 1 terms plus the 0 term, or a total of n terms. In total then, the limit is n copies of a to the n minus 1, which is n times a to the n minus 1. Thinking of the variable a as a point which could vary, we realize that all this says is that the derivative of x to the n is n times x to the n minus 1. And this is exactly what the power rule says.